All right, show of hands, who has heard of recursion before? A few people, cool. Okay, so recursion at a high level is basically this very inception-like idea that, hey, while we're defining a function, we can actually call that function from within the same function. And so that's a very strange idea at first, but it is actually really useful if we don't necessarily know exactly how deep our logic is going to go, and we can't hard code in all of the possibilities. We can basically write a recursive function that is able to apply the same logic over and over to determine if it needs to go deeper down a path or it has now hit a desired piece of data that it can perform some logic. That'll make a bunch more sense with some visuals in a moment. So then we'll also go over the call stack and how the call stack comes into play with recursion, which can be a very dangerous thing where basically we can have a function that calls itself and it never stops. And the moment you run it, you break your computer because it can't break out of that loop. So don't worry, JavaScript is protected that once we have about 255 calls in a row to the same function, it will shut off and stop that from happening. But theoretically, you could hack into somebody else's computer and get one of their lower system functions to call itself repeatedly, and the computer would never be able to break out of that cycle and would overheat. So we'll go into a countdown example and then one of my not so favorite factorial examples, which is a little bit more math-based. But recursion is extremely useful for traversing any type of data, usually arrays that have nested arrays and you don't know how many levels deep it could go, or objects where you have nested objects and those can also go on forever. Strings are great for practice problems here as well, but you don't necessarily need recursion to solve them in real life. Then we'll close up with tips for approaching recursion. Yes, Amani.
Since the factorial example isn't your favorite, do you have an alternative?
If we have time, I'm not sure how long this lecture is going to go because there's like 65 slides, but we will see. Yeah. Okay, so recursion occurs when a function calls itself. And it's basically alternative to iteration because we take in a set of data, we can mutate it a little bit by chopping something off or shortening it down and getting closer to what's known as the base case and sending it back into the same function that's already been set up to handle that type of data. In the real world, you may see recursion instead of iteration when it's easier to reason about. So if we're able to break it up into a bunch of small functions and then we can have this main recursive function that'll just call a few functions with readable names, rather than a long list of nested for loops, it certainly makes sense and it's easier for your brain to work that way, although not at first. So it's easier to read than an iterative solution as well because actually once we are able to strip down to these two paths, a base case and a recursive path, it makes a lot more sense to see it visually. And it won't negatively affect your performance too much. That's a key reason for using recursion. Some people get recursion happy as soon as they realize that they can do it. But because the dangers we said about the call stack, it can be a performance hog, and we'll talk about that. So the call stack, before we talk about recursion, we need to have a better understanding of what this thing is and how it works. So JavaScript is single-threaded, which means that it only runs one function at a time, which means basically you can imagine there's like a blinking cursor when your code runs. And that cursor will move across the term that it's currently evaluating. And the call stack is basically once we hit a function that we need to call, you can imagine that the blinker is waiting right there for that function to resolve itself. And now another function starts, and that's where the cursor is actually moving, and that's what it's currently processing. When that function is done and it returns a value, we now jump back out to the outer one and we plug that value in. So the call stack is the structure that JavaScript uses to figure out which function is at the top and which cursor is basically currently processing the single-threaded head. So whenever we call a function, it's added to the top of the call stack, and JavaScript is always currently executing whatever function is on top of the call stack. Any function that's lower than it is basically waiting inside its own scope for the higher functions to resolve themselves and return a value. So we have two functions here, first and second. On line 13 we call first, and on line 14 we call second. So before I run this program, I've got a big empty call stack. And it's basically processing the main loop. So the cursor starts over here, It saves these definitions. It comes down here, and we need to evaluate this first function. So you can imagine that right here, I'm waiting for this to evaluate. And so first would appear on the call stack over here. Right there. Then basically we hop into first. We go through here, we process this, we don't do anything, and we basically return undefined. Which means that this call over here resulted in undefined. So we can pull this off of the call stack, and we can replace this basically with undefined. That's what it evaluated to, but we don't do anything with it. Then we can move on to line 14. Question? Did I hear something?
Oh no, I was like, excuse me.
Oh, I'm sorry. So we resolved function first. It resulted in undefined. We did the log, and now we're moving on to line 14, which to evaluate this means we need to step into that function that's currently where the single-headed thread is, or single-threaded head. And we'll throw second back on the call stack as well. Second resolves itself, returns to undefined. We're back out on the main loop, and there's nothing on the call stack. Does that make sense? Okay. Yeah, so now we're changing it up a little bit. We've basically just moved the second call out from on the main thread into the first function. So when I hit line 11, what pops up on the call stack? First. And now I'm beginning to process it. I'm coming down here, console log doesn't really do anything. Over here, I hit second. So I basically need to pause inside of first. And I know I need to go do some other work. And I can only continue once I've finished what that other work is, which in this case is processing second. So when I hit second and I need to wait for this to evaluate, what am I going to throw on the call stack? Second. Second is now at the top of the call stack, and this is where JavaScript is currently parsing and running that code. So what does second result in? What does it return? It returns undefined, and so it can get popped off of the call stack. Basically, that value comes out here. We don't do anything with it, and now this cursor can continue. And to continue processing first means that I'm still inside of first, and that's what's on the call stack. What does first return? And so where does my cursor return to? Where do I continue to parse from at this point? Or not parse from, but move forward. Where is my program head?
Go to line 12.
Exactly, yep. So now that we've processed first and second, we're back out here and we can continue our function.
Wait, can you just go through again the part where we call second and it's undefined at that line 3 when you're in there?
So you mean, what do you mean is undefined? What are you referring to being undefined?
When we run second at that moment.
We do run second at that moment. So if I back it up a few steps, basically we come into first over here. We come over here to second. Now second, the function is not undefined. We have access to that. That's not what you're saying, right?
No.
Okay, yes.
I'm just,
So we step into second. And basically, what do functions return if they don't explicitly have a return keyword?
okay.
Yeah, it doesn't do anything. It returns undefined. So basically line 3 just evaluates to undefined. That does happen in the compiler. We just haven't set up anything to capture that bit of data. But that expression does need to be fully evaluated, which means we have to go through second until we hit a return keyword. Or don't, and then return undefined.
But it would log out I am second.
It will log out I am second, yeah. So that will pop up on the log before we drop second off of the call stack. Did I say a hand there, Sean? You good? Cool. Okay, so now let's say that we have a function countdown, which should take in a number, and it should decrement down to 1 and log that number out. So if I call this with 5, this is what I would expect to see on the console. Now let's refactor our solution. So let's write a function that takes a number and logs it out. So we've taken out some of the functionality of what countdown does, but we can achieve the same result by calling that function over and over again. What does the call stack look like when we're on line 10? Exactly. Yep. So before we've gotten down here on line 10, we had to fully process this one and this one, so they're off of the call stack. This is the only thing we're currently working on. We don't create any more function calls, really, so countdown 3 is the only thing that's sitting on there. And do each of these functions have their own scope? Yeah, they do. Each of them has their own scope, and they initiate num to be equal to whatever their argument was. That's important to keep in mind as we go through recursion, is that each subsequent call to the same function creates their own local scope and their own closures. So basically, last time manually, we hard-coded in there that we would call countdown again with a number that had decremented basically since the last time. But that only worked because we wanted to type in 5 numbers exactly and copy and pasted it for 5 lines. If I wanted to run the same function with 100, that's going to take me a lot longer to type that out. And then if my manager comes to me and says we need to do it now for 1,000, I have to go edit the code again and type out all those extra lines. So instead, we can write a function that will work with any number you ever give us, no matter how big it is, and we won't have to update anything. So instead of manually calling countdown over and over, why not have countdown call itself? And then call itself again, subtracting 1 from the number each time. Does anybody see anything that can happen here? It's going to go forever. So what does the call stack look like at this point? We've got countdown 5. We came into here. We come down here. We log that out, which we see up there. And now we're sitting right here. We need to wait for this to resolve before we can ever take ourselves off of the call stack. But it just calls countdown again with 4, which then we'll wait on line 9 again and call it with 3. And we're never going to come back from this. It's just going to decrement the number by 1 forever, and eventually maximum call stack size exceeded. JavaScript just protected you from your computer blowing up and never letting you do anything ever again. Yes, Danielle.
I just want to understand, like, how is it saving the new number? Like, how does it know the new number is 4?
So do you think that when we come in and the new number is 4, so inside of that call, is num still 5 out in this call?
Yeah.
Yes. Okay, so if you can imagine when I had the board here and we start a function, at the top of it we define what num is and it's equal to 5. Then when we call countdown again, that's an entirely separate box on the board. It creates its own scope and it initiates its own variables. And so the num that exists in there and gets set to 4 exists in a completely different place in memory inside the computer, that num at 5 and that num at 4 will never collide. On each call of a function, it establishes its own scope just for that iteration of the call. So each of these different calls all do simultaneously exist with their own scopes in which num has been initiated to a different number.
So, like, say, like, you had countdown, like, okay, so, like, when you do num minus 1, it's, like, referring to, like, line 12, and then it'll refer to, like...
Yeah, so on the first time, we initiate a countdown scope, and num gets set to 5.
Yeah.
In here, it's 5. And in here we say, hey, pass to countdown the result of this expression, which says, hey, look up what num is on my local scope and just subtract 1 from that value. And then that results in 4. So we pass down to countdown, which makes its own scope somewhere else and says, hey, my num is equal to 4. Num over here is actually still 5. This doesn't decrement 1. I mean, it doesn't decrement the number at all. This is just evaluating what's the result of subtracting 1 on whatever value that used to be, or is. 5 minus 1 is 4. But we don't do anything with that. That's not going to update number in that scope, and we create an entirely new number in the other scope. So that started off really well, and we got all this functionality. We were logging out numbers like crazy. But because our function was instructed to call itself every time, the function ends up calling itself forever until the computer runs out of memory. So how can we stop this from happening? Any ideas? When do we want to stop counting down? Okay. I'm sorry? Yeah, well, let's say that 0 is our stop. At 0, we're going to log out liftoff. And at any other number, we're going to log out the number and then pass it back into the function. So while is how we would do it if we weren't going recursively. But because we are going recursively here, we're just going to, we know we're taking in a number. And whatever that number currently is, if it's 0, we're going to log out one thing. Else, if it's still a number, then we're going to log out that number and then go recursive. So those are the two paths. When we're writing a recursive function, there's basically one path where the data justifies that we need to go deeper, which in this case is when we have a number that's greater than 0. And the stop case is when we hit 0. So we have to code that we know no matter what piece of data we get, we're somehow going to get closer to 0 each time so that this will eventually stop itself. So yes, if the number is less than 1, I guess not 0, we're going to log out done. But if the number is greater than 1, we can log out the number and then we can pass it to countdown. And we have to make sure we decrease it here because the same logic is going to get applied over here. And if we didn't decrease it and we passed in 3, 3 is greater than 1, so we come into here, we logged out 3, and if we just passed 3 in again, it would never end. So in this recursive path down here, when the num is greater than 1, we have to make sure that we do something to get closer to the base case, which in this case is making sure we call a decremented version of that number on the next call. That's a lot of words. Does that make sense?
Would the while loop work though? And that's it. Like we're trying to avoid using.
Yeah, I mean, so we could write this functionality using a while loop. We're making this a recursive example, so we're purposely doing it with recursion here. But if I did throw a while loop just on this code that was here, we're not actually updating the number at all anywhere in there, and it would never break the while loop.
You can't write a while loop that would do the same thing?
No, you can easily write a while loop that will do the same thing.
With recursion, no.
Well, it depends what you're trying to do then. Why?
Because wouldn't it be the, I guess...
Because if you call the same function, and that function has a while loop inside of it, now you have two different while loops doing what logic? We're basically building in a while loop here that basically says, hey, when the number is less than 1, stop. Else, while the number is greater than 1, continue performing the same logic. And just by hopping back into the function, it's basically a while loop. But if I added a while loop in here, it would have to be doing some other type of logic that we need, rather than repeating the recursive ideas, because then we would never break out of the call stack. Yes.
So technically, say we have an extremely large number,
Mm-hmm.
and you have two choices. You could either do the loop or the recursion. Technically, the recursion, would it be more efficient to use versus the loop? Or?
In this specific case? Okay, so that really comes down to technicalities of how you set up your loop. For your intents and purposes, no, they should be exactly the same. They should both run in constant time. But if you got really finicky into it, basically the amount of calculations that goes on inside would determine which is faster. And how some for loops are set up is that on every iteration of the for loop, it's checking a length. And if that length isn't cached, a for loop can be much slower than basically doing the same logic without constantly saying, hey, while my array length is greater than 0 or whatever.
Because like for some of these problems, or for a lot of them, there's a lot of different types of solutions, and I'm sort of wondering like later on which solution should you use.
Yeah, so
And how would you know?
I mean, it's a whole other topic basically on this idea of O notation. And basically it would be determined by the data that you're feeding into it and how you process that data. So some functions are basically read as constant time, which means for every one thing in my array, I'm going to do one thing. Some other functions can be exponential, which means basically if I get 10 words and I need to check each of the words, this has a worst case scenario of doing 10 times 10 calculations. So it's dependent on your data and how you set it up inside. But when you get the data and the architecture down to the same idea, which in the for loop and recursive, it's going to be, hey, we're going to do it once for every number greater than 0. Then in programming world, we say that those are the same time. Although there can be slight differences with the length and calculations, we don't talk like that when we evaluate how fast a program is. Yes.
Kind of like on that, is the if statement the best way to put a base case in, or is there another?
Yeah, I mean, pretty much it's simple, it's readable, and there are shorthand ways that we could write that. Like if you've seen the ternary statement, we could take out some visual noise here, but we're not necessarily going to hit any performance increases. This is about as simple as it can get.
Okay.
Cool. So when we call countdown with 3, what do I expect to see pop up on the call stack? Yep, well, I'm talking about the call stack, some are talking about the console, but it's very similar. Yeah, so in this case, countdown 3, we're still waiting here because the first call hasn't returned yet. Because the first call is still waiting over here for the call when we passed in 2. And then in there, we're still waiting for the time that 2 then subtracted 1 and passed in 1. And we see that reflected over here, that we are still evaluating countdown 0 right now. So now when I come in here and I'm going to log out done, we're not going to hit this else, and I'm going to return what? Undefined. So done does go on the console, but yeah, we don't do anything after that. We return undefined, which means I now jump back into the top of the call stack where I was currently evaluating, sitting right here, and I got back what? Undefined. Doesn't do anything. We now jump out of the else and we return undefined. And that starts the process all the way back down until eventually we hit over here and we take everything off the call stack.
I have a separate question with this again. What if we do want to have it defined as the number logging out? So like if it's return, how would we do the order for like the else?
Okay, we want to do what with the number?
So instead of console logging, we return the number.
Uh-huh.
Because if we just replace console log, it wouldn't work to the next step.
Yeah, I mean, we could console log right here. We could count down num minus 1. And basically, we know that we're going to get stuck here until any of our child processes begin to return to us. So then I could save the result of whatever those child processes did, and I could return it on the next line, or you could even return right here. Either way, those will happen after all the child processes have run. Now tomorrow specifically, we're going to talk about passing values around and returning them back. Today is more of these like useless console log examples, but I do have an example we could look at to have the idea. All right, so the two main takeaways from Countdown are that if we're doing recursion, we need a base case, else what happens? Computer crashes, can't do anything, yeah. And so your recursive case, the key component of the recursive case is that it must change the input so that we will eventually trigger the base case. The recursive case must get you closer to whatever you said that base case would eventually be. So in this case, that's when the numbers are bigger than 0, and we decrement it before we recurse. So returning from recursive calls. I guess we'll talk about it a little bit today. Recursion becomes more complicated when the function must return a value. So a good practice is to start by defining a base case and then calling your function with the base case to make sure that you get back the value you're looking for. Now that's kind of been a repeated idea of mine of like the basically actively debugging. And that's something you certainly want to do with recursion as well. Before we even get started coding, on pen and paper, we should figure out what the base case is, what the return case is, and what we would like to get back when we call it with the base case. And then test it. Test that you can call the function, test that you get it with the base case. Base cases often occur when there's a simple input that expects a simple output, which in this case was when the number was 1. We return done. I mean, we console log done, we return undefined. That's the one thing we know will always happen when we hit 1. So, factorials. Looking at this math reminder down here, does anybody have any ideas on what a good base case would be? Yeah. And why is that?
Basically because that's the lowest it goes, and you know that they both return the same thing, 1.
Yeah, these are the lowest possible values where we have a defined output. 0 and 1 is always going to be 1, whereas I don't know what 100 factorial is. So in any of those cases, we're performing an extra recursive call to go a layer deeper. So we want to set up our function to start with those base cases.
So you start with the lowest hanging fruit.
Exactly. We want to build our way up. If we try to go all at it and you just miss one part of this flow, you're going to hit that infinite loop while you're trying to debug it. How do we feel about base case and recursive case? I know that was only like one example before we jump into this. So we can do other examples later. Okay. So, like I said before, we should write down what our base case and recursive case are and have a game plan before we jump into writing the code. So we've decided the base case is if the number is at 0 or 1, so we want to handle that. And then test it. And so we see if we call factorial with 0 and 1, we get back 1, which is where we ultimately want to end up. So the base case is set. We just need to remember that our recursive case must bring number closer to 1 or 0, so we will eventually hit that base case. And there's a trick in that code over there that's showing you a pattern of what happens with factorials. So that's what my gripe is with this example, is that if you weren't familiar with factorials before, basically the factorial of a number is equal to itself times the factorial of the number directly below it. So in this case, factorial 5 is equal to 5 times the factorial of 4, I believe. So in the recursive case, we can test our function first with a recursive case and make sure that we're not hitting the base case, which is what they're illustrating here. Undefined. We haven't set this up yet to handle anything other than 0 or 1. Just good practice there. But in this case, if we haven't returned up here and we're outside of line 5, we know we have a piece of data that doesn't satisfy our base case, because we would have got out of there if it weren't the case. So down here, we can now call factorial again as the recursive case. And so if our current number is equal to 2, what do we want to get the factorial of? Yeah, because the factorial of 2 is equal to 2 times the factorial of 1. So they're just showing here that the recursive case in this case is going to be the number minus 1. And so they see that we're able to get the factorial of 1, but we returned undefined for the call of 2. Does that make sense, how we got 2 different values back out of here? We haven't really finished our function here. But it's a good example of undefined versus returning the number. Okay, so if we go back to that pattern we saw before, we saw that, yeah, we really want whatever the current number is times the factorial of the number decremented by 1. And so here we can see that the factorial of 2 is 2, but we're returning undefined because we haven't returned anything in that recursive case. So now that we figured out all the pieces, we can set up our return and get back that the factorial of 2 is 2. Okay, now with a call stack and a bigger number here, when we pass 5 into factorial, where does the cursor pause?
Line 7.
Exactly. And that's because it didn't satisfy our base case, so we didn't return. We're back out here for the recursive case. And we're saying, okay, let's save some piece of data called result, and it's equal to whatever this is going to evaluate to. I don't know yet. And that's going to be num, which we have, times calling factorial of num minus 1. And 5 minus 1 is 4. So as we basically plug 4 in here, we can now satisfy this entire function because we figured out the argument. So we need to go to that function. And so that was factorial 4. And that is what we now need to evaluate, and that gets thrown on the call stack. So then the process repeats itself while these numbers are greater than 1 and 0. Ultimately, when we're inside of the scope of this one, when we called with 2, we passed in, hey, factorial, get me the factorial of 2 minus 1, which is 1. So we go into that one, and here's where we finally return 1 for that base case. So this resolves to that 1 value, which means we now have 2 times 1 as a result, and we can return 2, which is inside of this call. So after we pop the 1 off, we can now return 2 times 1, which is 2. And that goes back out to the call that's waiting also on line 7, but in the scope where num was equal to 3. And that's how the numbers get built up on every single time that we return. It just gets multiplied to the current number. And it started with 1 or 0. Does that at least make sense how the call stack is being built up if we try to forget the math that's at work here? Any questions on that? Yes, Vahab.
Question for when you decrement,
Uh-huh.
why can't you put number minus instead of number minus 1?
Okay, so our end game goal in here is that we just want to pass in some value that's a decremented value of our current number. We don't actually care whether number gets changed in this scope or not because we're not doing anything with it after this. So to answer your question, yes, we could decrement number and pass that in here as well. But there's a difference between if we said minus minus num and num minus minus, like I think you said. And so, okay, so just to visualize that, if we're not plugging in minus 1 and we have num in here and we wanted to pass a decremented version of that, if we had minus minus num, it first decrements num and then evaluates to that decremented value. But if it was num minus minus, which is kind of a lesser known way to do it, that one would actually pass num in first and then decrement the value. So if you use the shorthand, you have to be aware of those two differences. But in the end, all we care about is what the evaluated value was that went into factorial. So we don't even care if num got updated after that, but we needed to get to a decremented num, which could have been done by saying, yes, minus minus num. Generally, I guess this is more acceptable because subtracting anything from num isn't part of our logic. It doesn't actually do anything for this function. So this is clearer that it's just that, hey, we just want 1 less than whatever this current number is, rather than needing to save the decremented value.
Why wouldn't this get to minus 1? Where's our sum?
Oh, so eventually once we pass the 1 in here, num is equal to 1 and we return 1. What was the question? Why we wouldn't get to
Minus 1.
negative 1?
Oh, yeah.
So like as this ever equaling negative 1?
Yeah.
Just we have a catch here that if it's ever 0 or 1, we're going to catch it there and return, which starts the return process all the way up. And so we never come down here to decrement when 1 or 0 is the num. We'll never decrement those and pass it in. So we've kind of just safeguarded against that.
I have a question. into set result to factorial 5.
Yeah, so in this case, we're not console logging out anywhere.
Right.
So result is going to be whatever the result was of the call that had 5 on it. And so that call was the first one to go on the call stack. And before it's fully evaluated, this is basically going to build up all of the lower results.
So it's purposely like the same as line 7.
Yeah, you're asking why don't we just return num times factorial num minus 1? Because we could do that as well, yeah.
You're saying why don't you just console.log factorial 5?
Yeah.
In line
Because,
12
yes,
instead of line
okay, so if we just drop this, and console log this,
Yeah.
we would log out what the eventual value was out of factorial 5. It's just that they're writing this example as to like be able to set up to actually use that result later on.
Okay.
But yeah, for all intents and purposes, if we just wanted to log out the value, we don't need to save it.
When I tried this on CodePen, it said that line 11 was already defined and like it was an error message. So result was already defined, so there's 2 less.
Yeah, I mean, this one is in its own scope, so unless there was something weird inside of CodePen, it shouldn't have freaked out about that. I mean, if the scopes merge, then that's a problem, or there's something hidden in there, but no, this should run fine. But if it still has a problem, show it to me after this, I'm curious.
Okay.
But CodePen has done some tricky things. Okay, so the 3 takeaways from factorials. Write your base case first and test it using simple inputs and outputs to make sure that you can actually hit it. As soon as you write your base case and you test it, input the results that, put in an input that would result in a recursive call. Wait. Yeah, as soon as you have the base case done, then test it with a simple recursive call, one that's just slightly outside of the base case. Then you can build up to more complex inputs. But basically, if you can make a recursive function work at 1 removed from the base case, it should work for anything else that's now 100 removed from the base case. So you can use recursion with pretty much any data type in JavaScript. If you're asked to recurse through arrays or strings, the base case is usually when the thing is empty or it has a length of 1. So imagine finding the sum of numbers in an array. If this was the function you were giving and an argument that has an array and just one value in it. Pretty much if the array length is 1, what do we want to return here? Yeah, we can basically just return the 0th index of that array. If the base case requires the iterable to have a length of 1 or 0, it must mean that every recursive case needs to get us closer to that. Or in other words, we're probably going to chop down that array on every call. Nested arrays can be approached differently, and that's, I guess, what we're covering tomorrow. So I can't emphasize enough, start with the base case, get that working. Then test a recursive case with simple inputs. That way your console won't go crazy and it won't be, thousands and thousands of calls. And it will make it a lot easier for your brain to be able to trace it out, whether that's on paper or with your console logs. Yeah, and we always need to ask ourselves, what type of thing should my function be returning? Base case and recursive case should return the same type of thing, especially if we're going to build them up and basically store memory that way. Whereas basically in the factorial example, factorial 2 is the first time we actually basically return a value, which was 2 times the result of factorial 1. Then that value gets multiplied to factorial 3. And so it's like each call kind of has the bundled result of all of the layered children below it. Use console logs or debugger to debug. And yeah, I'm not a fan of that. So real quickly, we can go over some more real life examples, what they would look like and what base cases and recursive cases would look like in those. This is just one quick example here that has, it's also not too usable, but it's an example of just processing an array. And so basically, this is a function that should take an array of words. While there are words to process, it should log out each word as well as the last word that was logged out. And so this one is meant to demonstrate how the scope changes throughout each call. So basically, the first time I'm going to call this, we have this array that says a sample sentence for a useless example. And basically, we're going to pass that array in as words. And we're not passing in anything as last word. So last word is going to be undefined. And so inside of here, we're basically just plopping out the current word. And we're going to log out the current word as well as the last word. And then we're going to basically replace this words array with a slice of 1, which in other words is going to do what? If we slice on the first index,
Takes from the first index to the end.
exactly. So in this first call, when we come in here with this long one, when we get down here, we're just going to replace words in this scope with an array that looks like this. And then, now that we've sliced it down, we've gotten closer to the recursive base case, we can check, hey, if we're not at the base case yet, so in other words, there's still words in here, let's call the function. So this is what my call stack looks like on the first call. When we get in here, though, we come down to line 41 and we replace words after we log some stuff out, which we'll see in a second. But we slice words down by taking out that first input. And then we'll also have a reference to the original word that we had. And so I can go to my next call to this function with a chopped down version of the words array. And I can tell it, hey, this is what my last word was. This is what you want to start last word at for when you need to log it out. And so if we run that, we can see that the first time the current word was A and last word was undefined. So then we added this to the call stack, and this is what's being processed over here now. So the first word to come out of words is sample, and the last word we gave it. We told it, hey, my last word was the word A. And we can see that we continue down until there are no words left. And these functions all return what? They all return undefined. They were all just waiting right here. So as soon as the child runs, it throws its stuff on the console. They pretty much all just spit back undefined instantly, and we empty the call stack. So this is just an example of how these scopes, on every call to last words, they have their own scope that they know words as, and they know what the last word was. And so passing in an extra argument like this is a good way to tell a child call, hey, this is a piece of info that you need to know about what I just did. And so that's how I was able to tell it what the last word was without needing to pass all of the words every time. Okay, so just base case and recursive case examples. If we want to count down from a number, when 0, we want to log liftoff, else we want to log the number, and our input is looks like a number like 10, what is a good base case idea here?
Number equals 0 return liftoff.
Yeah. And recursive case is just num not equal to 0. And so that call stack, very simply, it would be, we call it with 10, we call it with 9, we call it all the way down, 3, 2, 1, and then when we hit 0, we're done. So what about this? If we want to iterate through an array, but each index could have an array, which could also have arrays at any of its indexes. So at a high level, we want to loop through this array, and we want to process each element while keeping a running sum. What am I looking for? Ultimately, at the end of the day, what is something that I want to hit inside of this array that I could do something with it?
Want to add the integer.
So I'm looking for integers. That's my end game goal, is that I want to hit every integer inside of here, right?
Yes.
So my base case is pretty much whenever the current element is a number. Then I could just add it to a running sum. I don't have to recurse. But if I hit another array, I'm in the middle of writing a function that's set up to sum up any amount of numbers and give them back to me. So if I hit an array inside of here, then I can just pass that array into my own function because my function is set up to sum it. And so I'll wait for my function to go deeper and sum up that inner array, and then I can just add that onto my sum. And after I loop through this whole thing, I could return whatever the sum was. So that's a different way to think about the Bayesian recursive case, because in those examples, the Bayesian recursive case come from the actual pieces of data that we access, whether it's an array or it's an integer. And if it's an array, we need to go deeper. And so that's how you find the recursive case there. Similar example here, imagine that we had an object that basically resembles a bunch of subjects and their scores. And my goal was to sum up all of the numbers that exist as values anywhere on this object. How do I iterate? I want to iterate through each key and value. That's the main goal here inside of this function, right? When is it a base case and when do I need to go deeper?
Go deeper if the value is an object.
Exactly. So yeah, I'm going to loop through this main object, each of the key value pairs. If I hit a number, I can add that to my sum and keep going. Great. But as soon as I hit an object like this science object, I just need to send that back into the same function because this function is set up to sum up all of the properties on an object, just like our factorial was set up. So when I pass this object in, I'll get back 140. And then I can just keep going and pretend this was 140 and add that into my sum. These will make a lot more sense when you start to use them tomorrow, but I thought that a good idea was to see where else it heads and different ways to think about Bayesian recursive case. So this one is probably most similar to a chance that you would use this online or in the real world. And pretty much you have some HTML string or some XML string, something here that represents a bunch of folders. And these folders can have all sorts of properties inside of them, but I've condensed it down. Basically, we want to convert the function, we want to convert this folder structure into some data structure that we know that we can basically put back together to track which folder appears inside of which. Don't worry about this down here. Just pretend that you have some function that is able to basically take one of these things and tell you whether it has any children on it and what the name of that folder was. When does it sound like you can stop? Versus when do you need to go deeper? Exactly. So in the case that we hit this folder here, we still have a child. So we're going to need to recurse basically on whatever value I have this set as. We need to find out if that has any children. And when we hit stuff like this, we're good. We know that there's no child inside of here. We can continue to the next one. But when we hit one that has a child, we need to recurse. It's just a different way of seeing the same logic and figuring out how to figure out to chop down your data set or whether you have enough to do the work you're actually trying to do, which in this case is once we have a folder, we're just trying to convert it to an object. But if it has children, we need to convert each of those children to objects, and that's why we need to go deeper. Okay, any questions? Yes, Jolene.
Number 2, or 3 or 4, but basically base case. So, we went over what the actual base case and recursive case was for number 1. What is it specifically for number 2?
Okay, so pretty much the structure of our. So let's say like we have our array, right? So for each element in the array, we get the current value. Are you with me so far? I just did this really shorthand to use a for each and to get the current value immediately to me.
Yeah.
And so pretty much if we were out here, we have some sum. And in here we can say, hey, if, well, what did we say in English? What's the base case and what's the recursive case? We said we need to iterate through this whole thing and we need to reduce it basically to a single value. So now we have something set up that's going to take in this massive array here, and I'm going to get a reference to each as the current value. Now that I have a piece of data, I can decide if I'm ready to do work or if I need to go deeper.
So if array
Go type of array I.
Yeah, so if array dot is array of the current value, then we need to go deeper. So we'll just change that up. We'll say if it's not an array, we can pretty much say, hey, the sum is equal to this current value. I mean, plus equal to this current value. Else, we know we have an array in here, so we need to go deeper. And we would call my function with the current value, which the first time, this will be the first time we recurse, is when we hit that array there. So I just typed out a skeleton for what this logic looks like, but basically inside each function we would have a sum for the entire array. And when we find a current value, when we find an integer, we can just add that integer to the sum. Else we need to add to the sum the result of calling this function with that array. So when 4, 5 comes in, 4, 5 will each just hit the base case and add to the sum and return 9. That 9 would evaluate right here, and this 9 can now get added into the sum that's already processed 1, 2, and 3. This specific example right here is very important, and it's a great beginner problem that you'll want to internalize, but I believe that we will cover this much more in depth tomorrow. But if you're starting to grasp this one, or you get the chance to, that is a great foundation to be able to then tackle something like this, after which point this would seem easy. Recursion makes no sense at first, then it clicks, and then it gets way easier.
So I get the logic, and what I'm asking is, what's the difference between the base case and the recursive case in that example that's on line 79, 78? What are those asking for?
So over here, I was just asking for us to talk about it, but in this case, basically the base and recursive case I'm saying is, for this problem, it's dependent on the piece of data that we're iterating through. Whereas the liftoff function was just dependent on one single point of data, and when it reached 0, that was the base case. Here it's we have to decide whether we need to go deeper or we can do some work for every element that we get out. And when we have an integer, because we know we want to sum things up, the integer is great. We can add that into a sum. That's a base case. If we get an array here, I need to send it into a function that's set up to process an array. And that's exactly what we're in the middle of doing, so we can recurse. Otherwise, I would have had to have hard-coded, hey, if it's an array, now try another for loop. And that would maybe work for right here. But as soon as I get to here, we have a third inner array over here, and I would need to have another third for loop inside of there to get deep enough.
So for this specific example, the if and else, they're not really black and white with the base case and recursive case.
That's true. So the base case and recursive case, we need to more think about how it relates to our logic and our end game goal of what is the work that I'm actually trying to do.
So for the array one, when you actually return a value, it would have to be outside of the for each.
Exactly, that's correct. Down here is where we'd return the sum, because each of these functions is set up to take in an entire array and return a sum for that entire array. So when we come in here, we basically stop this outer call to make a call to the same function called SumUpArray, or whatever this whole thing is basically the function. And we would call with 4 and 5. And so now we have those two sitting on the call stack, where this is the one all the way at the bottom of the call stack, and now above it, it's called to my function with 4, 5. This array has been set up to loop through it. This function's been set up to loop through that entire array. So for each, both 4 and 5. And if the current value is not an array, then we can add 4 and we can add 5. And this will return 9 down here. which means that on my outer call, I was still waiting for the result of calling this function with this array of 4 and 5. And I got that back as 9, and I added that to my sum. But there's no, I mean, it's a for each, so I can't break it completely right here, right now anyway. But I'm not done. I did one recursive case, but that's not the end game of the goal of this function. The goal of this function is that I need to loop through the entire thing. And so that's how the structure of my program has been set up. I won't return until I've looped through the entire thing. So when your work is done is a little bit different than when you need to recurse and what the exact base case is. And that's actually one of the trickier problems at first, is differentiating that and how it relates to the specific problem that you're working on. So base case means you're ready to do work to achieve your goal. Recursive case means that you need to do a deeper iteration to be able to do the work you need to do. So those you can kind of identify, but then you need to structure a program and what is the overall goal of what I'm trying to achieve? And how does that then relate to where my returns are going to be and what each child call is going to do? So in this case, and in the case of the factorial, we're building up a consistent sum, and that's holding all the results of the lower calls pretty much. So the lowest call will eventually return, and that will be from the one at the top of the call stack, but then that one gets saved into the scope of the one immediately below it on the call stack, and it builds up all the way to get to the bottom. It's a lot of words and not a lot of visualization. We'll get there. Any other questions? All right, let's take a 5-minute break and get to it.